Alright, today we're going to talk about the converse of the Pythagorean theorem. We've already discussed the Pythagorean theorem in the last couple days, so now we're going to talk about the converse of the Pythagorean theorem. It's important that we remember what converse is. The definition of converse is that the converse of a conditional statement is a statement formed by interchanging the hypothesis and the conclusion of the conditional statement. Remember, the hypothesis follows the if, and the conclusion follows the then. So if we think back to the Pythagorean theorem says if we have a right triangle, then if I square the length of the hypotenuse, that will be equal to the sum of the squares of the lengths of the two legs. That's on page 441 if you'd like to reference it. So go ahead and write the converse of the Pythagorean theorem now. Pause the video and try writing the converse. The converse of the Pythagorean theorem we get if we interchange the hypothesis and conclusion. So you'll see now, if we have the hypotenuse squared, the length of the hypotenuse squared is equal to the sum of the squares of the lengths of the legs, then we must have a right triangle. Now in order to know, we wouldn't call this the hypotenuse if it's not a right triangle, so we always look for the longest side length, because if we have a right triangle, then the longest side length would be the hypotenuse. We know that if we have a true conditional statement and a true converse, then we can write a true biconditional statement. Write the biconditional statement now. Pause the video. The biconditional statement looks like this. If a triangle is a right triangle, a triangle is a right triangle if and only if the square of the hypotenuse is equal to the sum of the squares of the lengths of the legs. So now let's use this. Example 1 asks us to tell whether the given triangles are right triangles. When I look at this first triangle, I recognize that this is the longest side. So if this were a right triangle, that would make 3 root 13 the length of the hypotenuse. So that is what I test. So I want to know, is this statement true? And we find out that it is. 3 root 13 squared, I can think of this in two ways. I can use my properties of exponents and say that that must be 3 squared times the square root of 13 squared and simplify. Or I can recognize that when I square a value, it's just multiplying it by itself, in which case 3 times 3 is 9. Square root of 13 times square root of 13 would be square root of 169, and we can simplify there. So this is a right triangle. When we look over to the right, if this were a right triangle, 29 would have to be the hypotenuse. So we're going to test this with 29 being the hypotenuse. And when we do that, we see that the square of the longest side is not equal to the sum of the squares of the lengths of the other sides. So no, this is not a right triangle. But what kind of triangle do you think this is? If it's not a right triangle, then it is either an acute triangle or an obtuse triangle. Well, let's take a look at this. 841 is greater than 832, which means this hypotenuse, if I square that length, it is longer than the sum of the other two legs. So if this were a right triangle, this would have to come in a little shorter. This hypotenuse would have to be shorter. So a right angle would be here, but 29 being the hypotenuse forces this to open wider. So this is actually an obtuse triangle. So because when I square the hypotenuse, I get that value is greater than the square of the other two sides, I find that this is an acute triangle. We can actually use this now to determine whether any triangle is right, acute, or obtuse. So we know that if it's equal, then it's right. If it's greater than, it would be obtuse. And if it's less than, it would be an acute triangle. So let's take a look and put that in words. If I have a triangle ABC, and I label the lengths of the side opposite each vertex with a lowercase letter of that vertex, the longest side would be length C, and the other side opposite A, I will name that length A. I will name the length of the side opposite B, lowercase b. So if I take the longest side and I square it, and I end up getting that less than the sum of the lengths of the other two sides squared, then it's an acute triangle. If it's equal, I will have a right triangle. And if that hypotenuse squared is greater, then it will be an obtuse triangle. So we can now use this to classify any triangle if we're given the three side lengths. For the rest of the problems on the back, what I would like to do is have you pause the video, try the problem on your own, and then check my worked out solution. Do that for every problem to make sure you are understanding the problem in its entirety. Go ahead and flip to the back now. The problem is really asking you to do two things. First, determine whether this triangle can even exist, and then if it does exist, figure out whether it would be acute, right, or obtuse. So think back to the last couple of days. I know that this triangle only exists if the sum of any two legs is greater than the third length of the third side. I'm sorry, sides, not legs. So I have to try all of these out. Well, when I do that, I find out that if I add these two lengths together, it is greater than the third. The other two added together is greater than the third, and same thing here. So because all of these are true, yes, this is a triangle. These side lengths are of sides that would form a triangle. But now I have to decide whether this is right, acute, or obtuse. Well, if this were a right angle, or right triangle, then the 4.2 would have to be the hypotenuse. So I'm going to use that as my C. So I want to know, if I take 4.2 squared, how is that related to 2.8 squared plus 3.2 squared? And as I simplify, I find out that this value is actually less than the value on the right-hand side. So therefore, this is an acute triangle. Let's do the same thing for example 3. When I test over here for example 3, I find out that these inequalities all are true. Therefore, this is a triangle. I take the longest side, 11.2, that would have to be my hypotenuse if this was a right triangle, and I test that, and I want to know what would this be related to the squares of the other two sides added together. And I find out that that is greater than 92.66, therefore this triangle would have to be an obtuse triangle. Example 4 is asking us to do something very similar, so we're just getting some repetition with this. You first determine whether the numbers can represent sides of the lengths of a triangle, and then if they can, classify it. So still two parts. So for A, we see that yes, it can be a triangle. And when I figure out how they compare, they end up being equal. So this is a right triangle. Remember, this is a converse of the Pythagorean theorem. For B, I found out that this is could not possibly be a triangle because 15 plus 12 is equal to 17. That would be like if I had a triangle and these two sides kind of collapsed and they wouldn't even be able to form a triangle. It would just be fall and make a line segment. So we would have no height of a triangle. Let's move on to C. For C, we recognize that here, the square root of 8, if I don't have a calculator, I can still figure what this is about. I know that the square root of 4 is 2, and the square root of 9 is 3. So I know that the square root of 8 is somewhere between 2 and 3, but it's going to be closer to 3. So as I do this analysis, I can still, in my head, without using a calculator, determine that the square root of 8 plus 4 has to be greater than 6. And I determine that the rest of these inequalities are also true, so these three side lengths could represent the lengths of a triangle. So now let's see how they would compare. 6 would have to be the longest side, so we set up our inequality, and what we see is that 36 is less than 24, so this is an acute triangle. Finally, for part D, 28 would have to be the longest side. So when I set up my inequality, I see that, first of all, these can form a triangle. These lengths would form a triangle. And then when I test it, I found out that this would be an acute triangle. So this is how we can determine, given the lengths of a triangle, or a potential triangle, what type of triangle it would be, acute, right, or obtuse. What I'd like you to do now is take a look at the extra practice, because I think it extends your thinking further than what examples 2 through 4 do, and we'll discuss our answers to these in class. So these are challenge problems that I'd like you to try to come up with situations that would satisfy the conditions given below. Good luck!